when we begin talking about graphing rational functions, we realize that rational functions have asymptotes. And remember what asymptotes were? Asymptotes are lines that the graph comes exceedingly close to but never touches. Okay? Now, when we're talking about exponential functions, they always had horizontal asymptotes, but an asymptote could be horizontal, it could be vertical, it could be slanted. Okay? So we know what asymptotes are. It could be vertical, horizontal, or oblique is what we call them. That's another word for slanted. So they're at an angle. So before you even start graphing your rational function, you first have to think about what the asymptotes are. Okay? All right. Going back to what a rational function is, a rational function looks like this, where you pretty much have an expression in the numerator and you have an expression in the denominator. For example, if we go, if we go up here, right? A plus b over a times 1 minus b. This is a rational expression, right? This isn't a function, but this is a rational expression. You have one expression on top, one expression on the bottom. If I take something like that, and if I say, okay, now y equals 3x plus 2 over 2x minus 4, let's say, that now is a rational function. So I've got one expression on top, one expression on the bottom. Okay, now remember what a degree was, right? The degree is the highest exponent in an expression or in a function. Okay. When we talk about rational functions, let's first talk about what the vertical asymptote is. The vertical asymptote is all points where the denominator equals 0. So look here. We've defined the numerator as a of x, the denominator as b of x. So to find the vertical asymptote, you just set the denominator equal to 0. Okay? Makes sense? That's it. It's as simple as that. So once you do that, you will get points, and some of the time those will give you asymptotes, and we'll talk about when those points are going to be asymptotes and when they're not going to be asymptotes. Okay. Let's talk about horizontal asymptotes. To find horizontal asymptotes, we need to look at the degrees. Okay. We have to compare the degrees of the numerator to the denominator. If the degree of a, now was a the numerator or denominator? A is the numerator. If the degree of a is greater than the degree of b, no horizontal asymptote. Okay? I'll take you in a second. If the degree of a is less than the degree of b, the horizontal asymptote is y equals 0. If the degree of a equals the degree of b, then we just take the leading coefficients. Okay? What do I mean by that? So let's take a look at the first one. The degree of the numerator is greater than the degree of the denominator. So suppose I have 3x squared plus 2 over 2x minus 1. You see how the degree of the top is higher? That means no horizontal asymptote. Now, here, what if the degree of the bottom one is higher? What if you have 2x minus 3 over 5x squared plus 7. What would the horizontal asymptote be? Y equals 0. Now, if the degrees are the same, so suppose you have 3x squared plus 7 over 2x squared minus 1. If the degrees are the same, you set these, you put them on top of each other, and what does that reduce to? 3 over 2. So the horizontal asymptote would be 3 over 2. Okay? Questions? No more questions? Okay. Yeah. Here are some examples where in the first case, there is a vertical asymptote at x equals -1 right there. Right? That's a vertical asymptote. Here, you have a horizontal asymptote and 2 vertical asymptotes. Here you have 1 horizontal, 1 vertical. Okay. One common misconception that I want to knock out of the park first before we do anything else. When you've got a vertical asymptote, here let's say, there is no way under any circumstances that the graph could ever hit that asymptote. There's no way, no way, no way. There is no way. Okay? If you've got a horizontal asymptote, the deal with horizontal asymptotes is this. Horizontal asymptotes, this is how I abbreviate asymptote, take effect at infinity and negative infinity. That means if I've got a horizontal asymptote here, in the middle where x equals 0, 1, -10, 20, 30, -40, that's not where the asymptote takes effect. The asymptote starts taking effect at 1,000, -1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000. What do I mean by that? In the center, a graph can cross the horizontal asymptote as many times as it likes. It's only at the very ends that the asymptotes take effect. Okay? So here too, it could cross as many times as it likes. It's only at the end that the asymptotes take effect. Okay? I just want to make that clear. This is a very common misconception. All right? This. We're going to do lots of examples. Horizontal asymptotes take effect only at infinity. That's just how they are. Okay? Horizontal asymptotes, they don't start to materialize until the infinities. Okay? You'll learn later on that it's at infinity. They're only defined at infinity. Okay, let's graph our very first rational function. All right, so first, locate and graph the vertical asymptote. Okay, for vertical asymptotes, we set the denominator equal to 0. Now, in order for this, okay, so we solve this and we get x equals 1, right? In order for this number to qualify as a bona fide asymptote, it has to be such that in the original function, the x minus 1 cannot cancel with anything in the numerator. So, is there a way is there anything else in the numerator that can make the x minus 1 go away? No. That means, yes, this is a vertical asymptote. Okay? So, x equals 1, that's another common misconception, is here. Lots of misconceptions here. All right. So that's x equals 1. Okay. Part B. Locate and graph the horizontal asymptote. Okay? All right, the horizontal asymptote. What's the degree in the top? Less than that. It's 0. Okay? What's the degree in the bottom? 1. If the degree in the bottom is higher, what's the horizontal asymptote? If the degree in the bottom is higher, then it equals 0. Okay? So if the degree of the numerator is less, then it's 0. Okay? So it's y equals 0. So y equals 0 is here. Now, one other thing we have to check for is, does the function have any zeros? How do we check if the function have any zeros? We would have to set the numerator equal to 0. Now, is it possible to set the numerator equal to 0 and get an x value out of it? No, so there are no zeros. Okay, so now we need to graph this. Okay, so now we have two regions, the left of the asymptote and the right of the vertical asymptote. So we look at the vertical asymptote, that divides into two regions. Okay, let's look at the right of the vertical asymptote. Okay, what are our x values here? X equals 2, 3, 5, 10, right? For those x values, is the function positive or negative? So let's just test one. Suppose x equals 2, this whole thing would give me a positive value. So to the right of this, my graph is positive, it's above the x-axis. So here's how it looks. It's got to follow the asymptote. And here, that's how it looks. Okay? It's got to follow the asymptote there. It's got to follow the asymptote there. I'm eyeballing.
So we can just...
You can. Unless I've specified to give me like some specific points, you could eyeball it. Now, okay, you know those video games where the character like exits the screen and then he re-enters on the opposite side of the screen? It's sort of what like that one. If the graph exits upward like that, it enters from the bottom on the other side of the asymptote. So if it exits on top on the right side, it re-enters on the left side here. And it goes that way because there is no other way for it to go. Okay? You can look at it in a different light. Here, the values of x are -1, -2, -10. When you plug those in the main function, you get negative values, so it's got to be below the x-axis. Okay? All right, let's do one more. Part A. Is there a vertical asymptote? X plus 6 equals 0. X equals -6. Can that be an asymptote? Yeah, because the x plus 6 will never cancel. So at x equals -6. Okay? Any horizontal asymptotes? What's the degree on top? Degree is 0. What's the degree on the bottom? Therefore, what's the horizontal asymptote going to be? Y equals 0. Now, to the right, okay, are there any zeros of the function? No. Okay, to the right of the function, to the right of the asymptote, is the function going to be positive or negative? So when I plug in like x equals 0, will I get a positive or negative value here? Negative, right? Like the whole thing will be negative. So that means to the right of this function is negative. It's below the x-axis. So it looks like this. Okay? To the left of the vertical asymptote, x equals like -10, right? For those values, this is going to be positive. So it looks like that. Okay? Questions? Okay. All right, so take a look at this. Okay, what's the vertical asymptote? X plus 2 equals 0, x equals negative 2. Okay, what's the horizontal asymptote? He says 2, is that right? He is right. How is he right? How do we do it? Right. When the degrees are equal to each other, I just say 2x over x, and that reduces to 2, so y is equal to 2. Okay? Now, are there any zeros? How do I get the zeros? I set the numerator equal to 0. So I say 2x equals 0. X is what? 0. So at x, there is a 0. I'm sorry. At 0, there is a 0. Okay? Believe it or not, that just gave us a lot of information, right? Just by knowing that there is a point here below the horizontal asymptote, I now know that to the right of the vertical asymptote, the graph is going to be down here because it's got to hit that point. Okay. All right, so it's going to look like this. It's got to hit that point and come down. That means to the left of the asymptote, it's going to be above. Okay? Now, this works, right, where like one is below, one is above, as long as, well, I'll talk about that later. Okay. I'll talk about it when we come to an example like that. Okay, take a look at this one. So vertical asymptotes. Now we have lots of things to set equal to 0. Right? So x equals 1, x equals negative 4. None of those can cancel with the numerator. So there is one at 1. There is one at negative 4. Horizontal. Okay, what's the degree in the numerator, by the way? What's the degree in the denominator? No. The degree in the denominator is 2, okay? But still, the horizontal asymptote is y equals 0. What happens if you just say 0 for the horizontal asymptote? It points off. Okay? Now, are there any zeros? No. Okay, so let's graph this. Now we have 3 regions. Okay? What's the easiest one to pick where it's going to be positive or negative? Let's take a look. Okay, so here I have x equals 0. If I plug 0 into here, into the x's, is the value of the function going to be positive or negative? Negative. So that means in this region, the graph is negative, right? Okay. That means here, I'm going to follow the asymptote, go up. Now, watch the reasoning here. Can it hit the x-axis? No, because this function has no zeros. So what is it going to do? It's not going to stop. That means at some point it's got to turn back around and come down here. Almost. Then what happens? It goes up here like that. It goes up here like that. Okay, like how beautiful is that? Does everybody see why that happened? Okay, so do we know why it turned around here? Because it was, it's got to live down here and it's never going to cross, so it's got to do one of these loops. Now, on the right side, it went off the screen here. It's got to re-enter on the opposite side, but from the top. And we mirror that here. It went off the screen here. It's got to re-enter on the opposite side, but from here. Okay? Yeah. It's kind of like yeah, that's exactly what it's like. Yeah. Okay. Okay, so Vertical asymptotes. X equals -2, x equals 5. Is that right? Okay, what about horizontal asymptotes? So here's, okay, so what's the degree on top? 1, and the bottom? 2, so it's y equals 0, you mean? Okay, does the graph have any zeros? 2x equals 0, x equals 0. Okay, and there we go. That's an example of where it crosses the asymptote. You see that, Rafi? Yeah. Just cross the asymptote. Okay? Unfortunately, that tells us no information about like if it's going to be above or below. So let's just test a point. So for these positive values, you know, like x equals 1, 2, 3, is it going to be negative or positive? Like when x equals 1, I get positive there, negative there, so it's negative. In fact, how about when x equals -1? Negative there, positive there, negative there, so that's going to be positive. So that means here it's going to look like this. Huh? I know, because it can cross the asymptote as many times as it likes in the middle here. It's only on the very edges that it's not allowed to cross the asymptote. At infinity. It's literally mathematically defined as x approaches infinity, it takes effect. Within the realm of the function, no, like when you're at x equals 7, you're not at infinity. You're not even close. If you're at x equals 700, if you know closer to infinity than you are. Well, it depends, though, on the physical problem now that you're trying to solve, right? If you're talking about, like if you're talking about, I don't know, what are you talking about? If you're talking about, like, the life of, like, a bacteria or whatever, right? Like 700 days is huge. You see what I mean? Yeah, but mathematically, it does depend on the context of the problem. But basically, look, here, it's kind of clear cut. Because once you do this, on the left side now, is it going to be above or below? Yeah. Below. And here it's going to be above, right? So it's going to look like this. And it's going to look like this. Okay? Now let's get to, okay, so these had no horizontal asymptotes. I'm sorry, these had horizontal asymptotes. Let's get to the case where there is no horizontal asymptote. In that case, there may or may not be an oblique asymptote. Okay? So remember what we said, that if the degree of the numerator is greater than the degree of the denominator, we said there was no horizontal asymptote, right? Now, if the degree of the numerator is higher by 1, just 1, exactly 1, then there is an oblique asymptote. So if the degree of the numerator is exactly 1 greater, then we have an oblique asymptote. Okay? So, take a look at this one. Y equals 3x cubed plus 7 over x squared. Can there be an oblique asymptote? Yes, oblique. Y equals x to the 4 over x squared minus 1. Oblique? No. All right? And how do you find it? You have to do long division. Okay? So you have to divide the polynomial, and the oblique asymptote is the quotient without its remainder. Okay. Here, is there a vertical asymptote? x equals 2. So let's just put that here. Okay, let's talk about oblique. Huh? There is an oblique asymptote. We're going to have to divide this now. Okay? So it's going to be x minus 2 divided into x squared. X squared over x gives you x. We multiply, remember? X squared minus 2x. Now we're going to subtract. Subtract means changing the sign and adding. So I get 2x. Can I go one more time? I sure can. 2x over x is 2. I multiply. And you thought you were done with long division. Change the sign and add. That goes away. I have 4 left. Am I done? I'm done. Yes. As soon as the degree here is less than the degree there, you know you're done. Because x can't go into this. Now, the oblique asymptote is the quotient without the remainder. So this is the oblique asymptote. Okay, so that's the oblique asymptote, huh? No, we're going to graph y equals x plus 2 now. Y equals x plus 2 is graphed like this, right? You go up, y-intercept is 2, so you graph it like this. That's the oblique asymptote. Okay, tell me that's not cool. That's really pretty cool. You haven't even seen the half of it, but watch.
How do you know what the slope is?
Yeah. It's like y equals mx plus b.
So it's just 1 over 1.
1 over 1. Okay, we have 2 worlds here. The left of the horizontal, the left of the vertical, the right of the vertical. Okay, the right of the vertical is our function positive or negative? Like when x equals 5 and 10, when you plug them in here, the numerator is squared, it's always positive, and this is going to give you positive, so it's positive. So when x equals 5, how much is it? Huh? How much is that? All right, so we know x equals 0 there, and this has to be going like that because it can never cross the x-axis on the right of the asymptote, of the vertical asymptote. Okay? What about here? It has to follow the vertical, and then it goes back down like this. Yeah. Okay? Yeah. So here, okay, so what if, remember I've been telling you, you set the denominator equal to 0, and if there is no way for it to cancel, then it's a vertical asymptote. But I never said what happens when it does cancel. Well, here it is. What happens when it does cancel? Well, here we get a point of discontinuity. This is one point where there is a hole in the graph, right? And you either call it a point of discontinuity or it's a hole in the graph. This happens when the numerator and denominator have a common binomial. That means you can cross something out. So take a look at this one. When you've got something like this that you can factor top and top or bottom, let's first factor. So when I factor, let me factor next to the problem. When I factor, I get x minus 2, x plus 2 over x minus 2. These go away, right? So my reduced version of the function is just x plus 2. Okay, so what does that mean? All right. So now, is there a vertical asymptote? Well, we take x minus 2, we set it equal to 0 from the denominator, and we get that x equals 2. But what happened to that x minus 2? It's gone. It used to be a huge problem. There was a vertical asymptote there. But we were able to cross it out. We were able to make it go away. So this is called a point of discontinuity. So there is no vertical asymptote. Is there a horizontal asymptote? No, because the denominator goes away, right? So once you look here, the denominator goes away. So take a look. Once you reduced it, what does the function turn into? A line. Okay, so let's graph that line, x plus 2, right? So you go up to 2, that's the y-intercept, up 1 over 1, and we're going to graph that line, yes? Okay, so that's how this looks, except, where's my point of discontinuity?
2.
Okay, it's at x equals 2, y equals what? No. Plug x equals 2 into the reduced function. So y equals 2 plus 2, 4. That means at x equals 2, y equals 4, there is an actual literal hole in the graph. So there is only, I have to do that by erasing this. At x equals 2, y equals 4, 1, 2, 3, 4 here. Here's how we show this. You see that? There's a hole in there. Okay? And then there. Okay? Yeah. We plugged x equals 2 into here. That x equals 2 into that. Okay, now, this homework is due Monday.